Welcome back. So we continue our study of chapter 3 and we move to the next application of the mean value theorem, which clarifies the relation between convergence of a sequence of differentiable maps and convergence of the sequence of derivatives. Okay, so let us start by asking some questions. If we have a sequence of differentiable maps Fn, of course defined as usual on an open subset of an ordered space E into an ordered space F, if this sequence converges pointwise or uniformly to some limit F, does it follow that F is differentiable? First question. Okay, I want you to stop the video and try to answer this question on your own. It's very important to do this exercise. And I'll give you the answer, of course. Okay. So the answer is no. Why? This is an example. If you consider just the the sequence of functions defined on R from R to R, given by Fn of x equal radical of x squared plus 1 over n, then of course this is a sequence of differentiable maps because everything is differentiable. It's a composition of differentiable maps and the argument is not zero actually. So because the radical is not differentiable at 0. Okay, so Fn is differentiable and Fn converges pointwise to absolute value. As n tends to infinity, this is the radical of x squared, which is absolute x. Okay, and this is not differentiable. Actually, we can show that convergence is even uniform. Prove that as an exercise. It's very interesting. Why convergence is uniform? So even uniform convergence does not imply differentiability of the limit. Okay. Second question. Suppose that the limit, we know that the limit is differentiable. Okay. Does it follow that the sequence of derivatives converges to the derivative of the limit? I want you to pause the video and think a little bit of this question. Okay, true. And the answer is no. And this is one example. If you take the sequence of functions defined by sine nx over n, then of course if n converges uniformly to the zero function, which is differentiable. However, the sequence of derivatives is cosine nx, which has no limit. Okay. So convergence of the original sequence does not, even uniform, does not guarantee the convergence of the sequence of derivatives. Okay. Now, what about the converse? If the sequence of derivatives, if we know that the sequence of derivatives converges, let us say uniformly, does it follow that the original sequence converge first? And is the limit differentiable? Okay. This is, we're going to try to answer this. In general, yes, we have, but of course, to put some assumptions that guarantee this converse. Okay. So here are the main two theorems that we're going to prove. So we can work, of course, in a very general context between norm spaces, so we don't need to work on R. So the first answer to this question is, so we assume that all these functions are defined on a convex, on an open convex set, U. So U is convex. You will see why we need this restriction, and then we will remove it a little bit. Okay, we'll weaken it. So the domain of all these maps is convex. The target space is complete, and this is the second time where we need the completeness assumption. So F is a Banach space. Okay, for most of the results in this so far, actually, we didn't need the assumption of completeness. So this is why we just worked on ordinary norm spaces. Okay, but at some places we need the completeness assumptions. Okay, we already used the completeness assumption in chapter 2 when we proved the differentiability of the inverse operator. Okay, Third assumption, the sequence converges at some point. Okay, so there exists some point A in the domain such that Fn of that point converges to some limit. Okay, so in particular, this happens if the sequence converges pointwise. Okay, so at every point. Okay, this is what we usually have actually. And the last and most important condition is that the sequence of derivatives converges uniformly to some map. Then we can deduce that the original sequence converges pointwise to some map, of course, and convergence is uniform on the bounded subsets of the domain. And last and most important conclusion is that the limit is actually differentiable, and its derivative is the limit of the sequence of derivatives. So we can, if you like, we can interchange the operations of limit and differentiation. So derivative of the limit is the limit of the derivative, if you like. So in general, as we saw, these two operations are not interchangeable, okay, as we expect. But under certain assumptions, this is true. Okay, so the precise assumptions are stated as 1, 2, 3, 4. Okay, and I will give later some examples that illustrates the use of this theorem. Okay. So why this result is important, or why is it interesting? Because in many cases in math, we define objects as limits of a sequence or limits of a series and so on. So we don't have a formula, a closed formula for this object. So we cannot study directly differentiability. But this result tells us that we can say something about the differentiability if we put the right assumptions. Okay. And the next result is a little modification of the first result. So we keep the same conditions, but we replace condition 1. So we replace the convexity of the domain by connectedness. And we replace uniform convergence on the whole domain by a condition, by a weaker condition called local uniform convergence. Okay. What does this mean? It means that every point in U has a neighborhood on which the sequence of derivatives converges uniformly. Okay. So of course, clearly this is a weaker assumption than uniform convergence on the whole domain. And I will ask you to give an example later. And what are the conclusions? What are the conclusions actually? So we still have, so the same, the first conclusion is the same. So Fn converges, the original sequence is convergent, but in general we know that. So this is not the most important conclusion. Okay, so the original sequence converges pointwise, and convergence is also locally uniform. And the most important conclusion is that the limit is differentiable, and we can interchange the operations of differentiation and limits. So let us first prove Theorem 3.4, the first result, and then it will be very easy to deduce Theorem 3.5, which seems better actually, because we have the same conclusion under weaker assumptions. Okay, but actually we will deduce this theorem, this form, from the first one. Okay, so proof of the first theorem. Okay, so since U is convex, we can apply the mean value theorem, version 3.3, to the function fn of x minus fm of x. Okay, so I can write this as fn of x minus fm of x. You can call it g of x if you like. So this is g of x minus g of a, but rearranged in a little bit way. So this is less than the distance between x and a times the supremum of the distance between the derivatives. Here, this is fm prime, not fm. Okay, so Fn prime zeta minus Fm zeta for zeta in U. Okay, so this is the mean value theorem. Okay, so this is very important actually, because what does this imply? First, this implies that at every point x, the sequence of elements in capital F in the target space is a Cauchy sequence. Okay, and second thing, we shall prove that, don't worry. And so therefore, since F is complete, we have a limit. And actually, convergence is uniform on bounded subsets of U. Okay, so this is what we are going to prove now. Okay. How do I prove that this is a Cauchy sequence? I take an arbitrary positive number, epsilon, and I use assumption 4, which tells me that convergence, that Fn prime converges uniformly to the limit G. Okay, so this precisely means that the distance between Fn prime zeta and G of zeta can be made less than any positive number I like. Here I took epsilon over 2. It's not really important because I can take epsilon or. Okay, so and this happens for every zeta. So the same from a certain rank, of course. So and the idea of uniform convergence that you can take the rank independent on zeta. So it works for all zeta. So this is why we call it uniform. Okay. And therefore, if I take m and n bigger than n0, and I use the triangle inequality, I see that Fn prime is a uniform Cauchy sequence. This is just the triangle inequality, because Fn prime zeta minus U of zeta less than epsilon over 2, and Fm prime zeta minus U of zeta is less than epsilon over 2. So when I use the triangle inequality, I see that the distance between Fn prime zeta minus and Fm prime zeta is less than half epsilon plus half epsilon, and this happens independently on zeta. So you have a uniform, what we call a uniform Cauchy sequence. And okay, so therefore, if I go back to inequality 1, I see that the left-hand side is less than epsilon times the distance between x and a. Okay, for every n and m larger than n0. Okay. And assumption 3 tells me that at this point a, so Fn, we know that Fn of a converges to some limit. So in particular, it's a Cauchy sequence. So the distance between two terms of the sequence for large indices, say larger than a certain index n1. It's not necessarily the same as n0 as before, because it's a different sequence now. So for nm large enough, the distance between two terms is less than epsilon. So this is just the Cauchy condition, because Fn is convergent. So now if I take n and m larger than the max, the biggest between n0 and n1, because I need both inequalities. So I take n and m large enough, and I use the triangle inequality. So here we use a usual trick. So we add and subtract Fn of a minus Fm of a. So we get the distance between Fn of x and Fm of x is less than Fn of a minus Fm of a plus this quantity, which was the left-hand side of equation 1. So just add and subtract this term here. And according to what you said, so this is why we took the maximum, because we need both inequalities at the same time. So this guy is less than epsilon, and this guy is less than epsilon times norm of x minus a. Okay, so here if you fix a here, if you fix x and a is fixed by anyway, but if we fix x, then I can write this as epsilon times a constant actually. So this number, if epsilon is arbitrary, then this number is arbitrary actually. Okay, so therefore this means that the distance between Fn of x and Fm of x can be made arbitrarily small for n and m bigger than n2. So this precisely means that this is a Cauchy sequence in the target space F. And this is where I use completeness. Okay. This is why completeness is important. because it's easier to prove that a sequence is Cauchy than to prove directly that it's convergent, because you don't know the limit. Okay. So completeness tells us that Fn of x, for every x actually, has a limit, so it's convergent. So for every x we have a limit. So this defines a function actually that depends on x. The limit depends on x. So we get a new function f defined for all x, so defined on u. Okay, so, and of course, the fact that Fn of x converges to f of x means that this pointwise convergence for the time being. It's just pointwise convergence. Okay, so this proves the first conclusion. But this is not the most important one, actually. To prove that convergence is uniform on bounded sets, we use this inequality too. Okay, we fix everything, epsilon a, n, and x, and we let m tend to infinity. So everything is arbitrary here. So we fix everything and we let m tend to infinity. Okay. Since the norm is continuous, actually, so this guy converges, as you may easily check, to Fn of x minus f of x. If I fix everything and let m tend to infinity. So I get at the limit, because limits conserve inequalities. So Fn of x minus f of x in norm is less than, of course, I can factor by epsilon here. So it's epsilon plus epsilon norm of x minus a. Okay, so if now x varies in a bounded subset B, so of course then the distance between x and a in particular is bounded by a certain constant m, okay, as you may easily check. So this guy is bounded. When I say that x varies in a bounded set, then its distance to a is a bounded function. Okay, so therefore Fn of x minus f of x in norm is less than epsilon times a constant. This constant depends on b, actually. So this is why there is a difference between uniform convergence on bounded sets and uniform convergence on the wholes. Okay, because the m depends on b. So if I vary b, the constant may vary. Okay, so it may become very big, actually. So since this epsilon was arbitrary, this holds actually independent for every x. So the point is that m is independent on x, but it depends on the set where x varies. Okay, so this is really the meaning of uniform convergence on the set B. Okay, so this proves the second conclusion. Okay. To prove C, which is the most difficult part, so we have to go back to the definition and prove this condition. So f of x0 plus h minus f of x0 minus, for every x0 in U, near h equals 0. Now, of course, this is not the only way. We can write f of x minus f of x0 minus g of x0, x minus x0 is a small o of x minus x0. If you like to use this, it's the same thing, actually. It's not. Okay, so we use once again the triangle inequality. So we add and subtract this term, Fn of x0 plus h minus Fn of x0. Okay, and we add and subtract Fn prime of x0 evaluated at h. Okay, so this is just the triangle inequality. But this is true for every n, actually. But now we'll use it for n large enough. Okay, now we already used in the beginning the mean value theorem. We used it in a slightly different way here. So we used it for x and a. Here we use it for x0 a plus h and x0. So instead of a, I take x0. So because this is just Fm of x0 plus h minus Fn of x0 plus h minus the same thing but evaluated at x0. So It's a norm. This is less than the distance between x0 plus h and x0, which is norm of h, times the supremum of the norm of the derivative, okay, because u is convex here. And we already know that this quantity is less than epsilon. You can take the same epsilon for n and m. So take the same epsilon, the same n0 as before. Okay, so this is just the uniform Cauchy condition. Okay, so there's nothing new here. We already used this idea before. So the first term is actually less than epsilon times norm of h. This is the first term. Okay, so if in this inequality we fix everything and let m tend to infinity, then you get f of x0 plus h minus f of x0 minus this fn is less or equal than epsilon times norm of h. So this is the first term, actually, not this one. This is the first term. So the first term here is less than epsilon norm of h. Okay, now the third term is easy because fn prime x0h minus g of x0h is, by definition of the operator norm, is less than the norm of the, because these two guys are linear bounded operators. So this is the norm of the linear bounded operator times the norm of the argument h. Okay, this is standard. And since fn prime converges to g uniformly, actually, this is less than epsilon for n bigger or equal than n. We already used that before. So the third term is also less than epsilon norm of h. Okay, so now we have to tackle the second term here. Okay, but so we fix an integer n bigger or equal than n. So for example, take n equal n. It doesn't really matter. Anything would do. By assumption, each fn is differentiable on u. So in particular, it's differentiable at x0. So this the differentiability, the Fréchet differentiability condition implies that for h small enough, less than delta, the difference between, so the second term is less than epsilon norm of h. So when I put everything together, we get that f minus gx0h, so the f minus linearization, if you like, is less than 3 epsilon norm of h for every h whose norm is less than delta. So since epsilon was arbitrary, this is precisely the Fréchet differentiability condition at x0. But x0 was arbitrary, so f is differentiable everywhere. And this shows at the same time that the derivative is precisely g of x0, because this is the linear bounded term. Okay. Now, 3 epsilon, 4 epsilon, 100 epsilon doesn't really matter. Okay. If I wanted it to get exactly epsilon, then I should have taken here epsilon over 3 and here epsilon over 3, but this is not really important. Okay, so this concludes the proof of Theorem 3.4. Okay, so now we are going to deduce the next theorem, 3.5. And it's very important because it illustrates what we call connectedness arguments. Okay, so that I mentioned before, actually, in a previous video. So this is important because it illustrates the use, in a simple way, of course, the use of topology in analysis. So it illustrates the usefulness of topological concepts, and in this case, connectedness. So consider the set capital A of points x, where Fn converges. So to prove that, we want to prove actually that Fn is pointwise conversion. So we have to prove that A equal U. How do we prove that? We show that 3 things. A is not empty, A is open in U, and A is closed in U. So connectedness of U implies that the only possibility is that A equal U, and this means that Fn is pointwise convergence, or Fn of x converges for every x in U. So this is Okay, now the first point is trivial because by assumption 3, small a, fn of a converges. So this is why we need at least one point where fn is convergent. Okay, so fn of a is convergent, so small a belongs to capital A, and therefore capital A is not empty. Now, how to prove that capital A is open? We take an arbitrary point x0 in A, and we find a ball of center x0 totally contained in A. So this is the definition. Okay, so of course A is in capital U, so x0 is in capital U, and since U is open, we can find a ball of center x0 and radius r totally contained in U. And now we apply theorem 3.4 not to U, because we don't know that if U is convex or not, but we apply it to the open ball of center x0 and radius r. And instead of A in the previous theorem, we take x0, a point. So according to the conclusion of the previous theorem, Fn converges, and uniformly actually, because this is a bounded set. So it converges pointwise, and convergence is uniform on every bounded set. But since the ball is bounded, so convergence happens on the whole ball. Okay, we don't need for the moment uniform convergence, but we shall need it later. So in particular, Fn converges pointwise in this ball. Okay, so this means that this ball is contained in A, because every point, if x is here, and Fn convergent on this ball, then Fn of x is convergent. So x belongs to A. So we found a ball of center x0 totally contained in A, and therefore A is open. Okay, how to prove that A is closed? Well, there are two strategies. Either we prove that the complement of A is open, or we prove that A is equal to its closure in U, of course, because this is a relative. This is a relative closeness. Okay, because it's not true that in general A is closed in E. Okay, but it's closed, and it's relatively closed in U. So we take a point in the closure of A in U, which we know that is equal to the closure of A in the bigger space E intersected with U. Okay, we proved that in an exercise of topology. It's not difficult actually. Okay. Therefore, necessarily X is in U, and since U is open, we can again find an open ball of center X and radius R contained in U. But since X belongs to A bar, we know from the celebrated proposition 1.8 of topology that every neighborhood of X meets A. So in particular, this ball meets A, let us say at some point Y. So we choose a point Y in the ball of center X and radius R, and in A as well. So by definition, what does it mean that Y is in A? It means that Fn of Y is convergent. Okay. So once again, we apply the previous theorem to the open convex set Bxr with A replaced by Y this time. Okay. So Fn converges pointwise, and converges uniform on the bounded sets, but the whole space here is bounded. So conversion is actually uniform. Okay, so in particular, Fn of X is convergent, and so X is in A. So any point in the closure of A, in the relative closure of A with respect to U, is in A. So, and of course, A is contained in its closure, so we have equality. So this proves the third point, and we know now that, so this concludes the proof of the first conclusion A. Now, so since Fn is convergent, we know as usual that we can define a limit map. So for every x we have a limit, and we call the limit f of x. Okay, so we have a function now. And the remark that we said before, that actually converges is uniform on every ball in U. So this is precisely the meaning of local uniform convergence. Okay, so this proves local uniform convergence. Okay, now the last point, see, why is f differentiable? Okay, so we have to prove that f is differentiable at every point x0 and u. So we pick a point x0 and u and a ball of center x0 contained in u, and we apply the previous theorem to the open convex set, this ball actually. So on this ball, f is differentiable and f prime equal g, and that's it, because differentiability is a local condition. So differentiability on u implies differentiability on x0. That's it. So it's trivial. Okay, so this concludes the proof of Theorem 3.5. Okay, and so let me tell you that usually it's the condition of local uniform convergence is more often met in practice, okay, because a global uniform convergence is a much stronger condition. We don't always have it. Okay, I'll give an example now. So this is what we are going to do actually. You think of it. I will not give you the answer. So think of it a little bit. Give an example of a sequence of functions that converges locally uniformly but not globally uniform. Okay. And next exercise is a little bit more challenging, because we have now three conditions of uniform convergence. We have the notion of locally uniform convergence, uniform convergence on compact subsets of the set, and uniform convergence on the bounded subsets of U. If U is a if we have a sequence defined on an open set of a finite dimensional space, then all these three conditions are equivalent. This is not difficult actually. But the challenge is to see what happens if E is infinite dimensional. Do we still have equivalence? I want you to think on your own. Okay, if you really want to become a professional analyst, you need to get deeper into these nuances. Okay, now let me formulate a useful corollary, more useful actually than the theorems, which deals with series of differentiable maps. So if we have, I will call the general term of the series by UN. So we have now a series of differentiable functions. So we'll assume that U is connected, F is complete, and the series converges at some point, and the series of derivatives is locally uniformly convergent. Then the conclusion is that the original series is pointwise convergent on U, and convergence is locally uniform. And the most important thing is that the original series is differentiable, and we can interchange summation and differentiation. Okay, we know that, and you are encouraged to give a counterexample without these assumptions. So in general, if we don't put the right assumptions, this equation may be wrong. Okay, and this is the difference between a mathematician and a physicist. A physicist will tell you, well, this is trivial. Derivative of the sum is the sum of the derivative. Okay, why are you bothering me with your theorems? Yeah, but the point is that we can give counterexamples. Okay, so in order for this equation, this relation to hold, you have to put some assumptions, and these are the very general assumptions under which this is true. Okay, so why this is a corollary? Because you will do it, you will prove it, you will deduce it from Theorem 3.5. Okay, it's not difficult actually. Just I'll give you a hint. Instead of Fn, take sum of UK, k from 1 to n, and apply the previous theorem to Fn. Okay, so it's straightforward. Okay, so and now I will end this video with an exercise and an example. For a real number x bigger than 1, we set f of x to be the sum of, so the sum of the series of general term 1 over nx. So this is 1 plus 1 over 2 to the x plus 1 over 3 to the x, 4 to the x, and so on. Okay, now we know that this series is convergent, actually. This, you studied that in first year by comparing the general term to an integral, or the series to an integral. Okay. Okay, so there's no problem of convergence here. Okay, but the question is, so we don't have actually a formula or a closed formula for f. Okay, so the question is f differentiable? Okay, and this is what you have to prove. To use the previous corollary to prove that f is different, and this is not totally trivial actually. So this illustrates the usefulness of the previous theorems, that even if we don't have a closed formula for a function, we can still study its differentiability. Okay, and this example actually is a particular case of the Riemann zeta function. Actually, f is the restriction of the Riemann zeta function to the interval 1 infinity, because the Riemann zeta function is a holomorphic function defined on the whole complex plane without 1. And as you may know, it's very important in complex variable and in number theory. Okay, and for your general culture, the Riemann hypothesis that if you solve you will get $1 million states that the non-trivial zeros of this function, this holomorphic function, lie on a vertical line of equation, so x equal 1/2, if you like, on the vertical line x equal 1/2. Now there are trivial zeros which are -2, -4, -6, etc. Okay, the non-trivial zeros all lie in this vertical line. So this concludes the video and section 3.4. So thank you for your attention and see you next time.